All right, so our next speaker, it's a pleasure to introduce Francesco Tarantelli from Scuola Normale Superiore and University of Bologna. Actually, you're actually at University of Bologna. Your co-authors are at
exactly.
Okay, and he's going to tell us about a sea of coins. So please let's welcome Francesco.
Thank you, Sebastian. Thank you, Sebastian, for the presentation and the organizer for the organization. Today, I will speak about Proliferation in UniswapV2. And in particular, I will focus about the security and financial properties about these new tokens in the platform UniswapV2. For details about this work, you can see the full paper in this QR code. And so let's start with some fast introduction of about this work. Okay, a blockchain is a set of blocks that where the following one is connected to the previous one with the dash, and each block are deployed all the transaction in the same timestamp. In this environment, we can deploy the DEX, this is the external exchange, in which a user A can trade with a user B through a smart contract, in which are ruled all the rule of the DEX. For example, other market makers is a type of DEX in which the price asset is given by a constant product formula. And an important concept we will be using in the following is the input, which is a waiting node in which there are depending transactions that we want to deploy on the blockchain. UniswapV2 is a particular MMM in which, for example, the reserves of two tokens, the token A and the token B, are connected with the constant product formula, X for Y equal to K. And if now we want to create a token, in the creation, we also to create a pool page. For example, a pool page is a pool in which we put both the tokens, our new tokens, for example, Ethereum, in a pool, and we interact with this pool with different actions. That is a swap, a mint, a burn. So we have two different type of traders: the liquidity taker and the liquidity provider. Okay, that where the liquidity provider can mint or burn, and the liquidity taker swaps the token for the other. Okay. So now, how we can create a token? We write the smart contract about stuff. We deploy this contract on the blockchain. There are functions that mint this token, and then we use the library ERC20 to use the important function like total supply, balance of, so on and so forth, to describe the different behavior of this token and the market dynamics about that. Also, in this context, there is the owner, that is the trader that creates this type of token. Yeah. Yeah. Oh, okay. Okay. Yeah. Yeah. Okay. Perfect. No, too close.
No, that's
fine.
Yeah.
Okay. But okay. Okay. Yeah. Okay. Yeah. Okay. For example, this is an example of smart token related to the token called DOP, in which we have all the variables associated to the DOP. It's like a class in this example. And we have, in particular, we have the function inside this contract. This is the transfer function that rule how we can swap this token. It's important for the distraction, for the after distraction, for some security property about token. And this is the construct that we funds will be run when we deploy this contract on the blockchain. Yeah. So, yeah.
Want to understand, if I want to create a smart contract, I can do that, right? I can copy this code, create my Agostino token, and then I will deploy it. There is no restriction of security enforcement.
No, for the moment, no. Okay. So the data definition, we collect the data about swaps, mint, and bonds. The swaps describe the price behavior about our new tokens, while the file about the mint and bond, the liquidity behavior. We obtain this data using connecting with the Ethereum node via WebD3 using RPC provider like React and so on and so forth. And we obtain our data in a window between the 10th of October and the 2nd of December. We collect all the new tokens in the pair and wrapped Ethereum, and we obtain around a very huge number of tokens. 78,000 of these numbers. So if now we want to compute the distribution of these tokens, we obtain that we have around 300 tokens created each day, and about near 10 new coins. Okay. Now, if we want to compute the log returns about this token, the price after 1,100 of swaps with the initial price, we obtain very huge values of returns. For example, we obtain with a mean of around 10 to the 5% return, so very huge volume returns. Then one can say, I can write realize simple binomial strategy and obtain always positive profit. Okay. In fact, if we do that, we obtain from the figure that we obtain profit. So we obtain we can use this type of words to make money. Okay. But in our strategy, we not consider three different types of problems. The one is the security of our token. In particular, there are some new tokens that are unsellable. So if we buy these tokens, we don't have the permission to sell it. This type of tokens are called honeypots. We obtain different types of honeypots. For example, the simple one is when in our smart contract there is a blacklist in which some wallet addresses forbidden to sell tokens. Or for example, we have a whitelist in which only a small part of wallet address are to sell this token. Or for example, we have in the interaction transaction, we have a sales tax, which is a tax you have to pay to sell the token. As a token, and say if this tax is equal to 100%, we are not able to sell it. Okay. So we take our data of the different new token and we split this type of data in the sellable and honeypot token. Okay. We use the security external provider like honeypot.is and GoPlusLab, and we obtain that the major part, around 88% of tokens are honeypot tokens, for a very huge number of tokens. We define honeypot the tokens that in one time in their lifetime are detected like honeypot. Okay. So we introduced also an observable, a physical quantity called the net read value. That is the product between the cumulative sum, the amount of token exchange at if and then is swap. Okay. Dot the price at this. This is a quantity that describes the amount of money circulating at time. A token capitalization. Okay. Question. I don't know exactly it's the same. Okay. If now we compute this value for under after 100 and 1000 of swaps, we obtain a different behavior between honeypot and sellable tokens. We obtain that for the honeypot tokens, we have a huge number of this negative value. Is associated with the fact that the honeypots are attracted to traders to invest on it. If we have that the honeypot is have a large value, no, a trader wants to buy it, of course. But after 1000 swaps, we obtain a similar behavior of the sellable on the token because after 1000 swaps, the token, the honeypot creator removes all the gain. So of course, a lot of honeypot tokens don't arrive to 1000 of swaps. And also we have the fact a lot of that the traders, the common traders, are this honeypot or selected token. Okay, because it's simpler to detect if honeypot behavior if we have a lot of time to study it. Okay. So now if we want to compute all the total net read value, we will say, for example, after 10 swaps, the major part of the net read value is composed by the honeypot token. Then, when we've increased the number of swaps from 10 to 100 to 1000, we see that the major part of the contribution of the major part of this value is from the quite similar to the two types of token. Okay. Now, another important property of the net value is that if now we want to plot the liquidity at the last of all our tokens, we obtain a characterization of our. In particular, we have two types of clusters, where the most important is the second one, in which we have that for low value of liquidity, in the last swaps, we have a huge value of NC value. All this cluster is composed by honeypot tokens. It's associated with the rag put. Put is when the token creator removes the major part of liquidity of the token. Remain as only a small part of liquidity, and then when a swap trader do swaps, the price rapidly increases, and the entity value goes up. Okay, so behave. Now, if we redo the returns of honeypot and sellable tokens, we obtain a similar process like in the entity value, where we have a similar behavior. Okay. Okay. Now go forward to the second problem. The second problem is we not consider in our strategy the threat of sandwich attack. Like in the previous, a sandwich attack is when an attacker sees the victim buy on the mempool and try to praise their trades before and after the victim buy in order to obtain all the amount of the victim buy transaction. In particular, if now we want to compute the optimal sandwich, if we call, for example, with DEX the reserve of Ethereum in the pool, okay, and with delta X of A, the amount of Ethereum traded by the attacker, and with delta X of epsilon the Ethereum of the victim buy, to swap, we obtain that the maximum gain, defined as like the difference between the amount of the attacker obtained after the second swap minus the amount of the first swap. Okay, we obtain that the maximum is given by the equation 4. But the important of this formula is that the sandwich attacks are more convenient when the liquidity pool is equal. Okay. In fact, if X goes to, for example, to 0, we obtain a use value of the X of mass. Okay. In fact, now if we want to plot particular example, okay, we obtain that our approximation is very close to the maximum of the exact behavior of the profit, like we in the blue line. Okay. Now let's move on the last problem. Is that in our strategy we consider a time strategy and not a physical time one. So we invest after a swap and not without considering the time with the swap. In fact, if we do this, we do a clusterization of the normal price associated with this token, we see that every cluster increase in the first part of the swaps. Okay, like you can see. In particular, now if we want to understand if this type of algorithm can be used to detect and sellable tokens, we have that, for example, for 2002, we obtain that the major part of honeypot is on the cluster 1. So we can use this type of clusterization like a measure to split honeypot and sellable tokens with some of course. And now if we want to do same clusterization but in swap time, in which use a different algorithm, that is the dynamical swapping, in which was also used in some signals. Okay, we obtain that we don't have initial increase of the normal price, but we have that the major part of the tokens, the normal price rapidly goes down, and this is because the initial fix is associated with the put pressure that in the first block in which is deployed the token. So it's quite impossible to our transaction before this bot. Okay. And so in the conclusion, we employ this binary strategy, and we obtain 3 different problems. in our strategy, the presence of an honeypot, the risk of signature attack, necessity of the a physical time strategy that in which our profit goes down. Okay, and also the presence of both is associated with a very competitive market in which you have to be smart to trade in